Thank you so much. And thank you so much to the organizers for the invitation. I very much appreciate it. I'd like to continue to emphasize the points that John Furnell made and give some other situations that might be problematic for microanalysis. Microanalysis has been around for a long time. It's somewhat amazing to me that we can measure concentrations in 10 milliseconds. If you consider a pixel a single measurement, this is quite impressive. But we need to now look into more details into this process, as I will show. This is even faster than my Tesla Model S. So anyway, I want to continue here. Before we go for a drive, we want to discuss some situations that John has alluded to. One of the problems is we really need high accuracy primary standards. And by the way, I should mention, I'm going to try to talk slow. It's not my natural style, but I will go through the slides fairly quickly, but I will also post a PDF of this presentation on the Probe Software user forum, so you can look at it in your leisure. So this is something that the co-authors and I are working on, is to obtain synthetic homogeneous global standards that we can use so that every lab has the same primary reference standards. This alone will help many of the situations that John talked about. These standards can also act as secondary standards. In fact, our goal is to provide both a primary and a secondary standard. So in other words, 2 materials per element, so we can check this. And also these secondary standards can also serve as spectral interference standards and zero blank correction standards. We need to check our dead time calibrations. This is something that's often neglected. We often think of this as a factory adjustment, but we now know that there are severe nonlinear effects in our WDS electronics. And there's a recent paper that I've just published with John Furnell and others that just came out last week. And so you should check that publication in Microscopy and Microanalysis, where we discuss a new method for dead time calibrations and corrections, and I will discuss that further. We need to use modern matrix corrections. Most of them are pretty good. We have a problem with the backscatter loss correction, which I will not go into in this talk, but we also need to make sure we're using the latest mass absorption coefficients. This can explain some of the problems that we see in some analyses. For example, high totals in garnets, where you have magnesium in the presence of iron. And we need better background modeling for trace elements. This means we need to support curve background fitting. And I'm also going to talk very briefly about the MAN, or mean atomic number, correction, and MPB, or multi-point background methods. This is where we use multiple background points, which allows us to do a curve fit to the background. And it's also and both of these are iterative methods, so they can deal with problems with interferences and contamination. We also want to measure K ratios, not only on our instrument to make sure all our spectrometers are giving the same K ratio within statistics, but also that our comparison to other labs is consistent. And this is something that John Furnell, Rulian Moy, and Will Knocklis are working on. And we need to consider that maybe we haven't been tuning our pulse height analyzers properly. And this is something that came up during the development of the dead time correction paper, because we are going from a very low beam current to a very high beam current, which you can think of as going from a very low concentration to a very high concentration. And when you have large changes in count rate, then you're going to have a problem with your PHA tuning if it's not done properly. And finally, we need to have accurate trace element determinations. We need to correct quantitatively for spectral interference corrections, and we need to apply blank correction if necessary, as I will discuss. So these are the problems I'm going to discuss today. The problem has been seen by geologists. We know that different labs are producing consistently different results. They all claim to be correct, but they all disagree. And this is a new paper which you can check out in Journal of Petrology. And these differences are not small differences. If you look here in this next slide, you will see that we're talking maybe differences of 10%. So these are not small differences. We need to resolve what's going on here. Part of this is standards, part of this is dead time corrections, part of this is matrix corrections, and part of this is other aspects. And I will talk about some of this. But before we go on to best practices, I'd like to talk for a minute about an example of worst practices in EPMA. Here's an example from the recent literature that I would consider to be one of the worst cases of EPMA. So this is a paper that was published in 2017, and you'll notice they very nicely report the elements they're analyzing for, the crystals they're using, and what standard they're using. And you'll notice something. This person performed trace element analysis of nickel in olivine using San Carlos olivine as a primary standard. When I saw this, I couldn't believe it. And you can see that the concentration of nickel is only around 0.3%. And I would just say shock and dismay is the only words to describe this situation. Here you can see what they've done here. They're using San Carlos olivine as their primary standard for nickel. Well, what's wrong with this? A couple of things. For one thing, the variance from the measured primary standard is propagated proportionally to the unknown concentration via the K ratio. So if you have a K ratio where A is the unknown and B is the primary standard, then the total variance adds in quadrature normalized to the intensity. Now we can't do anything about the primary intensity, I should say the secondary intensity of the unknown, because that's what we're measuring. But we can certainly do something about the standard we're using. And if B is a small number, then it's going to amplify the effect of our variance on our resulting K ratio after we perform the division. But the second problem is even worse. The known concentration of nickel in San Carlos olivine is very, very uncertain. And I don't know if you can see this so well. Maybe I'll put it over here. But the nickel concentration is the orange circles here. And as you can see, they vary from about 1,500 ppm to over 3,000 ppm. This is not a small disagreement. And so depending on which grain of San Carlos olivine you're using, as John Fresnel pointed out, you are going to have problems. So the solution here is maybe use a pure nickel or pure nickel oxide primary standard. And the idea here is that not only do we have an accurately known concentration of nickel, but we also get very good statistics on it. Okay, I'm going to hide this thumbnail view here. All right. Now, let's just review. So what we're doing is we're converting our intensities to a concentration, okay? And so we have a concentration that goes from 0 to 100 weight percent, and intensity that goes from some non-zero number, because we have a background, of course, to some other larger number. So in this kind of a curve, we have our absorption, correction, if absorption is dominant, and we also have, of course, fluorescence, if fluorescence is dominant. And for our primary standard, or I should say for our major element, the corrections that we apply here are multiplicative. And the background, however, is a subtractive correction. And that's very important to keep in mind because it has to do with what standards we choose to use for a particular element. In fact, for the major elements, dominant effects, and of course, as John mentioned, we need to check our analytical total. And we do not want to normalize to 100%. And the dominant effects are the standard choice and its accuracy, its homogeneity, the matrix correction, and of course, dead time. For trace elements, the dominant effects, we want to check 0. And the dominant effects, and that's the blank correction, the dominant effects are the background correction and spectral interferences. So always keep that in mind when you're designing your analytical setup. So let's start with the major elements first. This is a multiplicative correction. Again, the dominant effects are the standard choice, the matrix, and the dead time. So the accuracy of all three of these things is what affects our major elements the most. And this is a multiplicative correction. So the error gets smaller. The relative error stays the same, but the absolute error gets smaller. And so as we approach zero, and at zero, of course, it's a zero error. Now, that means that a 2% relative accuracy error at 100% yields a 2% to 8% absolute error, but a 2% relative error accuracy error at 100 ppm only yields a 2 ppm error for trace elements. So these multiplicative effects are not important for trace elements. I'm speaking generally, of course. This is a rule of thumb, and there's always exceptions. So we need to check our major element accuracy using a roughly matrix match secondary standard. It doesn't have to be a perfect matrix match. The matrix corrections are actually pretty good. For trace elements, though, it's a subtractive correction. The size, the relative size doesn't change, so that if we have an absolute 100 ppm, I should say the absolute error doesn't change. A 100 ppm, as you read here, this we're going to get a 100 ppm if we have a 100 ppm error at zero concentration in our background correction, we're going to have only a 100 ppm error still at the major element. So this is insignificant when we're measuring major elements. So we need to, but we can check the trace element accuracy using a zero blank with, again, a roughly matrix matched high purity material. So the best practices for standard selection, we want a homogeneous material, high purity, use a primary standard with the highest concentration. We don't want to extrapolate. For example, for magnesium K alpha and natural olefins, we want to use synthetic MgO or synthetic Mg2SiO4. Now, this assumes that you're using your dead time calibrations are accurate, your standard is accurate, and your matrix corrections are accurate. And for checking accuracy, again, use a roughly matrix match standard. So here's, again, the point I'm making again. Now, for trace elements, it's a little different. We also want to use a high concentration standard. Okay, matrix correction doesn't matter so much, but the background correction does. So we want to check the accuracy of our ability to measure zero. Can we measure zero? And if we do not get zero, when we try to measure zero, we need to make a correction for that. That's called the blank correction, and I published this in 2011 in American Mineralogist. Doped trace element standards are the wrong way to go. They tend to be of uncertain accuracy and homogeneity, therefore they are not useful. As an example, if we're measuring titanium, trace titanium in quartz, we could use a synthetic TiO2 primary standard and use a synthetic SiO2, could even be a synthetic SiO2 glass. But all we need to do is check the accuracy at zero. And of course, as John pointed out, we need to check for secondary boundary fluorescence situations. You can use the free CalcSAF standard software, and it will also allow you to calculate nominal interference corrections as well. What matters for trace elements is the background correction and the interference corrections in general. So John talked about standards. Well, you know, the problem with standards was recognized centuries ago, and this is a problem that continues today, as I showed in the work by Penny Weiser. So we are using standards that are often just natural materials with natural heterogeneity, with natural variation, and this is not a good situation. So we need to deal with this, and this is, I'm going to appeal to you. I'm going to have a slide up here in a minute. I'm going to appeal to every lab in the world, every microanalyst in the world. Search for better synthetic standards. Talk to commercially first, companies that are producing these materials commercially, synthetic minerals. The synthetic metals, pure metals are pretty widely found, although there are problems with those as well. But we can do better. This is some work from Will Knockless and John Fresnel and others, and he showed this problem already. I'm not going to go into this then, but there's problems even there's even for synthetic materials can have problems, so we need to make sure these are actually what they claim to be. But even in non-mineral minerals, we can have heterogeneities. Here's an example from Will Knocklis's lab, John Fennell's lab, where they found almost 3 weight% iron in a purportedly pure rhodium metal. So this is obviously some kind of a thermocouple material that had been sold as pure rhodium. So that's not a small error. And then, of course, we have people who are reporting commercial standards by using EDS and normalizing to 100. This is obviously not a good idea. So this is a global scientific scandal. I think we should all be ashamed of ourselves that we have not fixed this before. But we need to find these materials. I wrote here kilogram quantities. Of course, even 100 or 200 grams would be wonderful. But we need to get these materials, locate them, characterize them, and distribute them. And this is something that we're working on. So I'm proposing that this happen, and we're waiting for some funding. Will Knocklis is already pursuing some investigations on his own. We started a round robin with a few synthetic materials and got very good results. So we're very heartened that this is something that's going to work. As I pointed out, some of these materials are already commercially available. We can buy them off the shelf. We just have to make sure they are what they're claimed to be. But other materials may require development. For example, wouldn't it be nice to have a high purity synthetic stoichiometric zircon, or even a zirconia without any yttrium in it? And obviously, all these other things would be nice too. So some of these may have to be synthesized at academic or national labs, but I'm hoping that maybe some of these have already been done. Maybe these are some materials that are already sitting in a cabinet somewhere in your lab. And so this is an appeal by Dale Newberry from NIST saying, look around, talk to your colleagues, ask people you know who are crystal growers, find out what they might have, and let us know. If we can find even 200 grams of some of these materials, this would be a game changer for the microanalysis field. What we have currently today is like a pre-metric system. We do not have the same standard in every lab. It's really quite a bad situation. Okay, so we can also use these synthetic standards for lots of other purposes. So I'm not going to go over this again, but these would be wonderful standards for all sorts of tests, and not just as primary standards or secondary standards, but for other kinds of measurements. So let me just kind of review this major element practices. We want to use high accuracy end member standards. We do not want to extrapolate. We want to interpolate between 0 and the high concentration. Use a matrix modern correction, check your dead times. And we want to avoid large area crystals unless we're using a modern nonlinear dead time correction. And I will discuss that. This just came out last week. Please check it out. I think you'll be surprised at how large a difference it can make. In terms of the secondary standards, we need to check accuracy. And so this is an example, and this is the way my software has always reported results. So in here we have, as you can see here, let me get the cursor up. So here's the average. So this is what we measured. We measured 4 points. Again, a single measurement is not a scientific measurement. You always want to get an average and a standard deviation and a standard error. And when this is printed out, we also, because it knows that this is a standard, it also looks up what the published value is. So we can immediately see, okay, we have a 0.2% relative error in our silicon. Okay, well, that's acceptable. The sodium maybe is a little bit off by 10%, but you'll also notice that it's less than a standard deviation from the accepted value. Less than 2% on the aluminum, and so on and so on and so on. And we have a good analytical total. So this is the way you want to check for these things. And in case you're wondering what these numbers are here, these are the standards right here. Whoops, let me go back. These are the standards right here. 336 is an ethylene, and 162 is in this mineral glass. 374 is an orthoclase, just so you know. Okay, so how do we go from X-ray counts to weight percent? I'm not going to discuss this in any detail, but the important thing to remember is that we start out with intensities, we make a first approximation, and we perform the various corrections, background correction, hopefully an interference correction, and we get a K ratio. And this might be that we're doing MAN background correction or off-peak correction. We might do an interference. We use an interference standard for the interference correction, and we have our primary standard to get our K ratio. Do a matrix correction, and then we check convergence on all of these things, and we iterate until we get a result. And it should be pointed out that this double iteration here, this double iteration loop, is because we can correct for the, because when the interference correction is applied, it could change the composition of the elements in the material. And that means the matrix correction has to be recalculated. If you do the matrix correction, if you do the interference correction in like Excel, by just subtracting, you're not going to get an accurate matrix correction, as John discussed, for missing elements. It's the same problem. All right, so and this procedure here is true regardless of whether you're doing pixels or points. It doesn't matter. It's the same thing that's applied. And as I will show you, we do this method for points and pixels, quantitative pixels and quantitative points. So here's an example. So here's a map of oxygen in a iron titanium oxide. And if you look at this map for oxygen and you look at it, you would say, oh, look, this high intensities out here. There must be a whole bunch of oxygen out here. All right. I'm sorry. Must be a whole lot of oxygen in this red region out here and low oxygen here. Well, what if we quantify this map? Okay, let's quantify the map. Well, now we see a completely different story. All right. So this is now a completely different interpretation of what we would have given this material. This map is background corrected, dead time corrected, matrix corrected, and interference corrected. Quite important for oxygen. As John talked about errors for unanalyzed elements, so I'm not going to talk much about this, just to point out that this is essential for accurate mineral characterization. And we want to calculate all of these. For example, here's the question that someone asked about missing water. The gray dots are without the matrix correction for water. And when we include water in the matrix correction, we get the black dots. And this agrees with the FTIR data, as you can see right here. So here's the gray uncorrected for matrix correction. So even the concentration of water changes by about, if you have about 4% water and you don't add it to matrix correction, you're going to be off about 1% absolute. So like a 25% error. Okay, carbonates and carbon carbonates John talked about. An example from another mineral that he did. And I also should point out another kind of more subtle thing. If you're measuring halogens, for example, fluorphlogopite, and you calculate oxygen by stoichiometry, you're going to have too much oxygen in the calculation. You're going to have a total of, say, 104%. And that's going to affect the concentration of fluorine by a significant amount, because fluorine, of course, is very absorbed by oxygen. So you need to subtract out the oxygen equivalent in the matrix iteration. And that's something that we do in our software. John mentioned TDI or volatile corrections, beam sensitivity corrections. This is an extreme outlier case of an amazingly beam sensitive material. It's a sodium silicate glass made by NIST, originally to study, I think, storage of radioactive waste. And this is a log scale here, as you can see. And yet we don't have a straight line. We have an exponential curve on log scale. So this is a double exponential correction. This is a very severe correction. And in the case of silicon, it's the opposite. The silicon intensity increases over time. And this has to be extrapolated back to 0 time, which we can do. And everybody should be doing this. There's no excuse for not doing this. I'm not going to go over this, but just to point out that each of these methods is documented, and you can apply this in the software. So yeah, so this is just the things you need to do. It's just, some of you know this, some of you may not, but it's important to do. And beam sensitivity is very often encountered, especially in carbonates and hydrous materials. Okay, and by the way, I was surprised to see this. Even trace elements have beam sensitivity. This is a trace chromium in lawsonite, and here's also trace chromium in phengite. And these are just intensities, but this is showing over time there is a change in the linearity. So we're getting a slope, positive slope in both cases. So as the longer we measure our trace element, the more apparent concentration we see. So that obviously this needs to be corrected for. Here's an example of a TDI correction for an X-ray map. Here's a quantitative X-ray map where we have not performed the TDI correction. So this is without a TDI correction. By the way, TDI stands for time-dependent intensity. We don't want to assume that we know why the intensity is changing over time. We often have said volatile correction in the past, but it might be that the element isn't actually volatilizing, it just might be migrating. And in fact, in most cases, the positive ions will go deeper into the sample due to the subsurface charge, whereas the negative ions, like hydroxyl, will actually be pushed to the surface. So you'll obviously get very different effects due to the differences in absorption path. So here we see, and not only do we see a very low number for the sodium concentration here, but we also see this grid pattern here. This is complicated to explain. It has to do with ion migration as the beam scans across the sample, but we're getting only 1.8% of our expected concentration there. Whereas with the TDI correction, you can see that we're getting about 3.5%. So this is, again, not a small error. And you'll also notice here that we don't see that grid pattern. We have the TDI correction has corrected this on a pixel by pixel basis, and it has actually corrected for it. Also notice the same thing is true for the potassium, as you see here. Here you can actually see it happening in real time. This is the first frame, second frame acquisition, and you see, because we have a sodium mineral here that's not changing in beam exposure, you see the sodium intensity apparently getting smaller over time. That's from the same map you saw before. And then here are the pixels from the whole area. So the pixels here are from the actual melt inclusion, and the pixels here are from the quartz, which is essentially zero concentration. And here we have the next thing I'd like to talk about, which is dead time in WDS spectrometers. Normally, we don't want to correct, recalibrate the dead time. We assume the factory has done it, but the problem is that the factory may not have calibrated the dead time at levels sufficient to show the effect. So we have all seen this problem where we have a linear response up to a certain point in terms of the beam current, and then it drops off. So this is a nonlinearity that we need to deal with. And when we have large area Bragg crystals, like on modern EPMA instruments, this becomes a very big problem. So how can we calibrate this? Well, John Purnell and I realized that there's something we can do about this. And so let's look at that. So we know what a K ratio is. Everyone knows what a K ratio is, right? It's the intensity of the unknown or secondary standard relative to the primary standard, okay? Obviously corrected for dead time and background. Now, typically, these intensities will be different. And if they're different, the dead time correction will be different because they're different count rates. So the problem is that we want to make sure that this K ratio is the same not only on every spectrometer of our instrument, but also from one lab to another. This is the reason for using standards that are primary reference materials globally. So we will find that we might not be able to agree on these K ratios even when using the same standards, and this is the dead time correction. So there's dead time calibrations, there's PHA adjustments, there's all kinds of problems that might come to this. Spectrometer alignment, sample tilt, asymmetrical Bragg diffraction, which are essentially differences in the effective takeoff angle, are other causes. I'll talk a little bit about these. But here's the question. Should the intensity K ratio remain constant as a function of count rate, that is beam current? If I measure a K ratio at 10 nanoamps, do I get the same K ratio at 20 nanoamps, at 40 nanoamps, at 60 nanoamps, at 200 nanoamps? I should get the same K ratio at any count rate. So let's test that. So we have our linear dead time expression, which we all know. And this has been around since 1937, if you can believe it. But it assumes a linear relationship between count rate, input count rate, and output count rate, which is a good assumption up to a certain count rate. If we go up to a higher count rate, though, we can see that while we're at the lower count rate, we get a fairly linear response here. As we start getting up to 50, 60, 100 nanoamps of beam current on a large PET crystal, this is a Joel instrument from Annette Vonderhand's lab, we can see that we start getting a very nonlinear behavior. The K ratio should be constant. It should always be 0.55. In this case, I think this is looking at TiO2 versus Ti metal. And it doesn't really matter what the K ratio is. We can argue about that, but it should be constant over the entire range of beam current or count rate. This is just the K ratio. That's all we're doing, plotting K ratio on the y-axis and beam current on the x-axis. We call this the constant K ratio method because we should get a horizontal fit here. We should have a flat line right here if our dead time correction is accurate. And we start to see it going south at about 50,000 counts per second using the traditional dead time expression, which everybody's using except me, or my software, I should say. So this is what the Joel factory calibrated the instrument using, and it's good up until about 50,000 counts per second. But then the wheels come off, and so why is this? Okay, well, we could say that maybe our dead time calibration constant, which was 1.32, is not accurate. So let's put it up to 1.6. Well, what we're seeing here now is we're overcorrecting the low count rates and still undercorrecting the high count rates. So obviously this is not the approach that we should use. We have a nonlinear response in the system. So back in 1993, I noticed that some researchers who were actually calculating dead time for neural networks added a second term to the expression right here, as you can see. And we tried that and we get a better result. Now we can get up to about 100,000 counts a second. Well, that's an improvement. So once we realize that this is an infinite series, we can then apply this correction. And in fact, we can actually integrate this into a logarithmic expression. And this paper is already out, as I mentioned. And so let's apply that now to our original data. So we still have 0.55 for our low beam currents, but as we go to higher beam currents, we have a slight decrease in the K ratio. Not a big decrease, but a small decrease. Well, that's because when we calibrated this dead time expression, the dead time constant using the linear expression, there are some nonlinearities even at low count rates. They just weren't noticeable because we have here a very sensitive measurement because the y-axis can be expanded indefinitely to give us better sensitivity. So what we need to do is adjust this dead time, using the logarithmic expression. And what we'll see if we do this, because the dead time is actually a parametric constant, is another way of putting it. And it depends on the expression you're using to fit it. And here's what we get when we adjust it to 1.29. So we decreased the dead time constant by 0.03 microseconds. So a tiny adjustment. And now you see that we have the more variation at the lower beam currents and less variation at the high beam currents, but it is essentially a constant over a wide range of counts, which is, by the way, up to about 400,000 counts per second. Think about what this means for your high-speed mapping. You can do trace elements and major elements with high accuracy at high beam currents. If I look at a number of different spectrometers, if I take those plots that we just saw, sorry, one spectrometer, if still spectrometer 3, and I take those plots we just saw, here's the traditional linear expression right here. Here's the slight overcorrection using the logarithmic term, and here's where I adjusted it to 1.29 right here in the green there. And so you can see we're doing quite well. This is all in the paper that is just got published last week. We can also use, and by the way, the key thing here is that we measure the primary and secondary standards at the same beam current so that there's no picoamp meter nonlinearity. The picoamp meter is nulled out. Any nonlinearity in the picoamp meter is nulled out because we measure the primary standard and the secondary standard at the same beam current. So here's where we now use a single primary standard. And this is my Kamika instrument. And we found we had about a 2 or 3% error in the picoamp meter linearity. So by using a single primary standard and looking at all our secondary standards, we can see there can be problems. And this is a NETS JOL instrument. And you can see it's pretty darn good using a single beam current measurement. Okay. And I also should mention that we need to reconsider our PHA tuning. I'm not going to go into this in detail. We discussed it in the paper. But basically, what we want to do is measure our PHA at the highest count rate that we are going to utilize, which means the highest intensity, which means the highest concentration at the highest beam current. If we do that at 200 nanoamps, we just want to make sure, because of pulse height depression, that our peak is completely above the baseline voltage. And when we go to a lower beam current, yes, it's going to shift to the right a little bit, and it looks like it's being cut off here a little bit, but it doesn't matter because we're measuring in integral mode. Now, there may be situations where we have to use differential mode, but I say for most situations, we don't need to use integral mode, and we're going to get much more accurate results, especially at high beam currents. Because these counts look like they're being cut off, but they actually are not being cut off. In integral mode, the instrument continues to count photons all the way out here. We've increased the bias and the gain all the way out where we don't even see a peak and we still get the same intensity. So this is something that I hadn't appreciated until just recently. Yes, this is okay in integral mode. Now here's an example of an olivine mapped at 200. The standards were required at 30 nanoamps and the unknowns at 200 nanoamps. And you can see we're getting like 400 ppm single pixel detection limits. Of course, if we, and I should point out that our totals are actually around 99.5%, or 99%, 99.2%, but we're not measuring all the trace elements, the minor elements that we should. But it's still, and the stoichiometry came out great. I should have shown an example of that, but I didn't. Anyway, we're getting great detection limits. And so just to wrap up the constant K ratio method, I'll do it here. There's the logarithms expression. And checking to see if you can produce a constant K ratio over a range of beam current is an essential test to check for not only the dead time calibration, but also your picoamp meter calibration. And it also, you need to check for the agreement from one spectrometer to another spectrometer. Do all your spectrometers give the same K ratio? If they're tuned up to the same element at the same beam current and same beam voltage, they should give the same K ratio. So I'm going to go a little bit into trace elements here very quickly because I think I'm running out of time. John talked about secondary fluorescence. I won't talk about it. This is an example of titanium adjacent in quartz adjacent to TiO2 rutile. This example here was talked about by Castang 60 years ago, which is measuring cobalt in copper adjacent to cobalt. And this is not electron diffusion. This is secondary fluorescence. This was, we published a paper on this in Chemical Geology in 2018. You should refer to that. This is the software. This is the more recent version of the software that John showed. And here's an interesting one. This is when, and John actually published a paper on this. This is where you're measuring a major element in a fluorescing situation next to a material that doesn't fluoresce, or where the fluorescing element isn't present, and you actually can get a negative artifact. That's very important to note. This is discussed on the Pro Software user forum in quite a bit of detail if you're interested. So spectral interferences, you have the classic interference here of element A being interfered by element B. And how do we deal with this? Again, I mentioned the matrix correction iteration where we calculate that. Basically, it's this. It's here's the normal, K ratio with the matrix correction for the standard and the unknown. And then we also have here's the unknown intensity, standard intensity, here's the K ratio itself, the correction for both, and the concentration of the standard. And this is the correction for the interfering element relative to an interference standard. That's the S bar concentration right here. So by measuring the apparent interference in a standard that contains the interfering element, but none of the interfered element, we can actually calibrate this exactly. And this was actually published quite a while ago. So here's an example. So here's an example of a chalcopyrite and pyrite measuring molybdenum. Okay, so I'm measuring molybdenum. This is without the interference correction. And so you can see we're getting what appears to be, I'll show you in more detail in a second here. Here it is. So here we have without the interference correction, pyrite, chalcopyrite, getting about 1.9 apparent weight percent of molybdenum in the pyrite and 1.2 in the molybdenum. If we apply the matrix correction, the interference correction, I'm sorry, quantitative matrix correction, apparently they're statistically similar. And in fact, the real interesting thing is that this phase here is actually the molybdenum bearing phase. So again, we can do this, we just have to apply it. And that was published actually in 1993, but we've applied it to maps now as well, quantitative maps. These are actual concentrations. These are not just color values. These are actual weight percent values. Molybdenum weight percent, molybdenum weight percent, and without the correction and with the correction. All right, and then complex backgrounds. I'm not going to talk too much about this. This is when you have lots of rare earths present. There's two ways to deal with this. One is we can not measure off-peak. We can just measure a calibration curve, if you will, of the background. This is Kramer's law, basically. And we now have a very accurate way of predicting the background based on what we call the Z-fraction method, which is another paper coming out hopefully in a week or two. You can also use the MPB method, where we actually iterate and find the lowest backgrounds for a given set of measurements. So the backgrounds that are circled in red are the ones actually utilized for the fit, and the ones here are not utilized for the fit. And the program can do this automatically, which is pretty impressive. And by the way, I should just mention that the advantage of the mean atomic number background correction is you actually get better statistics, and it takes half the time. So here's an example of a map that took 20 hours using off-peak maps to calibrate the background. And here we threw away the off-peak data, so it only would have taken 10 hours to do. And you can actually see we're actually getting somewhat better statistics, as you can see. So this is amazing to get better statistics in less time. This is all explained in my 2016 paper, which is right here. All right. So again, you know, we want to check for traces and make sure we can measure zero. This has been known for quite some time. There are artifacts in our background due to the Bragg crystals, secondary diffraction, or even absorption edges in the sample. So we need a very high purity blank that's roughly matrix matched to check this. And if we do that, what you can see here is that we get very good sensitivity. I'm measuring titanium on 5 spectrometers. And you can see we're getting detection limits that are, you know, pretty good. This is 10 ppm, you know, even 5 ppm, 7 ppm. These are pretty good detection limits, okay? So not bad. But which one of these answers is right? Here we have a negative 28 ppm. Here we have positive 1 ppm. Here's a positive 7 ppm. You know, which one's correct? And the answer to that is only when you apply the blank correction. We have excellent precision, but which spectrometer is correct? Which is the right answer? And for that, we need the blank correction. Blank correction is very simple. And the interesting thing about it is the blank level doesn't have to be 0, although it's easiest if it's 0, because 0 is the easiest thing to measure. We know if an element's present or not, but if it's non-zero, the difficulty is knowing what is the actual value that's not 0. So I prefer 0 blanks, but that's up to you. This was published in 2011, as I mentioned. And if we do that, we apply the blank correction. Okay, now our numbers are all very much in agreement. They're within the standard deviation. Okay, it didn't change our detection limits. It didn't change our sensitivity, but it did improve things. And here you can see the blank correction applied from another sample, which was a pure quartz, synthetic quartz. and here we go. We're getting now same sensitivity as before, but we can do better. We can do better. We can actually combine the intensities from all 5 spectrometers into one spectrometer. And this is, you have to do this for both the standards and the unknowns so that it acts like one giant spectrometer. And when we do that, now we get something very interesting. We've taken all these intensities and we've combined them here, and now we're getting a 99% confidence interval t-test of about 3 ppm. That is pretty impressive. Okay, and the actual content of this guy is around 1.4 ppm as measured from ICP-MS. So within a standard deviation of the actual value. And we can also apply this aggregate correction to maps as well. Here's a map of sulfur in a otolith. And then when we combine multiple spectrometers, you just get better sensitivity. So we're measuring the same element on more than one spectrometer. All right, so I think that's all I was going to talk about today. I hope I did okay on time. So yeah, so just to, you can read this, but I think that we need to think about some of these things. We need to get the standard situation in hand. This is really an important thing. If you can help us, if you can locate commercial or academic or national lab sources of pure synthetic materials, we would be very interested in that. This would be for a global effort to get every microprobe lab in the world on the same standards. We want to perform these K-ratio consensus measurements, not only on our own instrument, but on intra-laboratory, but also inter-laboratory testing. I didn't talk about the Z-based backscatter correction. That's on paper that's coming out soon, but we soon will have a much improved electron loss correction for high Z materials that's going to provide much better accuracy for ore geology, sulfides and things like that. We can do our dead time calibrations, improve them using the constant K-ratio method, and using the log expression, we can correct for the nonlinear effects in our electronics. We can use the TDI correction for beam sensitive samples, both for our standards and our unknowns, by the way. And sometimes these TDI effects are also orientation sensitive. It depends on the orientation of the material. For instance, micas have a very different TDI effect depending on how the grain is oriented. We need to have better background models, and we need to think about our PHA tuning. I should have mentioned this before, but basically the idea is always make sure that your PHA peak is fully above the baseline level at the highest intensity that you're going to be measuring. And then when it goes to a lower intensity, the peak will shift to the right, but if you're in integral mode, that will not matter. You will be okay. And we need to do interference corrections and zero blank corrections. And please contact me or Will Knocklis for more information. Go to the forum, and I'm going to post this presentation on the forum as soon as we're done with any questions that might be here. And so you can read about and discuss on the forum any questions you might have. I'd be happy to answer them now or later. Thank you so much.